If you have paid attention during the derivation of the Van Hoff equation, I used the assumption if this is true, then this will be true. But some students may wonder, Dr. H, how can you know if this is true? This will be true. On the other hand, some students may wonder, Dr. H, to me, if this is true, this must be true. This is obvious to me. Let me show you the rigorous proof from here to here. Then I'm going to explain why we need rigorous proof from here to here. In other words, from here to here is not obvious. You need to prove that. Actually, I'm going to prove more than what is needed to derive the Van Hoff equation. I'm going to prove the second relationship because the first relationship is a special case of the second relationship. What I want to prove is if partial g over t, partial t at constant p, equal to negative h over t squared, then partial delta g over t, partial t at constant p, will be equal to negative delta h over t squared. If the second one is true, why the first one is also true? Delta G means the change of Gibbs energy of any process. This delta G reaction is the change of G of a chemical reaction. So delta G is more general than delta G reaction. Delta G reaction is also equal to the Gibbs energy of the final state minus the Gibbs energy of the initial state. But the final state of a reaction is the product. The initial state is the reactants. Well, let's get started. By definition, delta G means the change of Gibbs energy. We use the Gibbs energy of the final state minus the Gibbs energy of the initial state. Let me put it down. We can use GF minus GI to replace delta G in this partial derivative. Let's see what we can get. Mathematically, we can break this down into two terms. From the property of partial derivatives, this partial derivative can be turned into two partial derivatives. From Gibbs-Helmholtz equation, the first partial derivative is equal to negative hf over t squared. The second partial derivative is equal to negative hi over t squared. They have the same common denominator. We can combine this into one term. The enthalpy of the final state minus the enthalpy of the initial state is defined as delta H. Then we can prove the second relationship is true. Well, let me address the original question I asked. Some students may wonder if without delta this is true. Is it always true with delta? Let me make up a story. Let's assume partial g over t, partial t at constant p equal to negative h squared over t squared. Partial delta g over t, partial t at constant p will not be equal to negative delta h squared over t squared. We will use similar steps as what we did for the derivation here. I'm going to show that if this is true, this is not true. From this equation, the first term is equal to negative hf squared over t squared. The second term is equal to negative hi squared over t squared. Then we can use negative hf squared over t squared to replace the first partial derivative. We can use negative hi squared over t squared to replace the second derivative. These two terms have the common denominator. Then let's combine them together. Apparently, hf squared minus hi squared is not equal to delta h squared. I hope this additional work will not confuse you. My purpose is I want you to know that if some relationship is true, you cannot assume that the change of that relationship is also true. From this relationship to the change of the same relationship, you have to rigorously prove it.